everyone, my name is Brianna and I'm an environmental geology major in the Earth and Environmental Science Department. I'm going to be presenting on my capstone project, which was developing a sediment pollution and nutrient pollution pilot study in Hazel Run. So the specific aims of my project is to utilize in situ sensors that measure turbidity and conductivity so we can conduct a model-based assessment of sediment and nutrient runoff in the Hazel Run tributary of the Rappahannock River. An introduction of some topics I'm going to be talking about is a little bit of background of the Chesapeake Bay and what BMPs are, why they're important, why Rappahannock River and Hazel Run are a good option for this project, why in situ sensors are so important, the equipment that we're going to use, the deployment methods and sample collection, as well as information on the model we're going to be using and how to develop that model, and the future directions that the project has potential for. So the Chesapeake Bay is a highly polluted watershed. There's an image on the right showing its expanse, and the leading cause for the pollution in the Chesapeake Bay is excess sediment. Excess sediment does things like block light from reaching photosynthetic organisms, cover the organisms that live on the bottom of the rivers and streams, and it also carries toxins. Toxins can bind to sediment particles and therefore get carried into the streams as well. The leading cause for excess sediment and the subsequent degradation of the ecology is humans. Humans do things like urbanize landscapes through development and clearing of land for agricultural purposes, and in the past few decades there's been even more growth and more urbanization, and all of this urbanization leads to impervious layers, which lead to excess sediment because it increases runoff. Impervious layers prevent water from going into the subsurface ground beneath it, and so the water has to go across the land to reach its rivers and tributaries. And when the runoff crosses the land, it picks up things like sediment and toxins and other pollutants and carries those into the rivers as well. So organizations like the Chesapeake Bay Program and the United States Geological Survey use best management practices to help prevent or reduce pollution. These are things like the barring of certain practices and maintenance procedures that are placed upon different companies, organizations, and people to prevent excess sediment and other pollutants from going into waterways. Some types of BMPs include treatment requirements for materials before they're disposed, certain operating procedures to prevent the creation of the pollutants, as well as structural features, so physical things like barriers, dams, fences, anything that will block the sediment or pollutant from reaching the waterways. So the Rappahannock River is also impacted by high amounts of sediment. It's listed as the river that has the highest annual sediment yield of the rivers in the Chesapeake Bay watershed, and it only has one monitoring station compared to the 24 monitoring stations of the James River. So therefore, a lot less is known about the Rappahannock River, which makes it a great river to study and learn more about. In addition, the Rappahannock River has been experiencing high amounts of urbanization. One of the results of this is an increase in nutrient loading, which may eventually go into the bay. Additionally, because the land has been cleared around the river, it makes it a lot more susceptible to damages from things like high temperatures and increased rainfall. So as a result, the water quality of the Rappahannock River has been deteriorating in the past few years as a result of the increase in urbanization. In fact, in 2019, the Friends of the Rappahannock found that the Rappahannock fell 19 points in its report card, which is an evaluation that the Friends of the Rappahannock gives that talks about the overall health of the river and its local tributaries. So while little is known about the Rappahannock, even less is known about the tributaries that flow into it, which are equally as important and significant into the overall health of the river. So the Hazel Run has an excellent location for us to conduct the study because it's close to the university, which makes it easy for us to access the equipment we're going to be using and the data. It also goes through different zones, including downtown commercial Fredericksburg and residential zones and highway zones, all of which have high amounts of impervious layers. It also has been experiencing high amounts of urbanization in recent years. Additionally, it's listed on the 2020 Impaired Waters list of the Virginia Department of Environmental Quality, and the Friends of Rappahannock gave Hazel Run the worst grade out of all the tributaries to the Rappahannock with a D+. Its worst grade, an F, being in land use because of these impervious layers. So that makes Hazel Run a great place to conduct a study because of all of the concerns surrounding it and its location. One important feature of this project is that we're going to be using in situ sensors. These are sensors that we can place in a location and leave, and they will continue to collect and store data on their own. So that means we don't have to go and physically collect samples ourselves. They're relatively inexpensive, which means we can deploy more of them, and we can also measure multiple parameters at a singular location for a relatively low cost. Additionally, they continue to collect samples. So whereas with manual samples, you're limited in the amount of samples that you can reasonably collect, the sensors continue to collect and store data. And lastly, most importantly, they can collect data during high transport events. These are things like storms and floods when a large amount of water is being discharged and a large amount of sediment is being transported. These events are very unique and very variable, and with in situ sensors, we can learn more about them and collect data on what's actually going on, whereas with manual samples, it can provide dangerous conditions for the researchers, and they can happen very quickly, and we may not be able to collect data or get a true sense of what is going on during these events. So the main piece of equipment we're going to be using is an EXO3 sonde, which is an in situ sensor. We can equip the sonde with different types of sensors depending on the data we want to collect. So we are going to be using a turbidity sensor and a conductivity and temperature sensor. We will also be using a wiper that cleans the sensors to help prevent fouling and sediment buildup. Some accessories include a guard to protect the sensors, a USB cable to collect the data, and whatever equipment we're going to need to deploy these sensors. So there are two main categories of deployment. When you deploy these sondes, you really have to kind of get creative and do what you can with the environment they're being deployed in. But the first popular category is suspension. So this can be from a bridge, this can be from a wire hung between two trees, and it's really good to use in locations with deep water or where the bank space is either limited or erosive. The major benefit to this method is that you can easily access it if it's attached to a bridge. The next most popular method is some form of anchoring. So the sonde is attached to something that's attached to an object on the bed of the stream or in the bank. This is good to use in locations with narrow channels or steep banks, and it's likely going to be the deployment method that we will be utilizing by driving a signpost into the bed of the stream and attaching the sonde to that signpost. It will help keep the sonde away from the banks and in the water. At the bottom, there's an image from YSI, the producer of the sondes, where someone is collecting the data from a sonde. So in regards to samples, we're going to be collecting samples weekly. So first, we are going to collect data from the sondes, as well as maintain them, clean them, get rid of any sediment debris, or buildup and make sure nothing is caught in the wires. And at this time, we are also going to be collecting manual samples. These samples will be sent to a laboratory for analysis. And samples and data will be collected more frequently when a high transport event has occurred. So a big storm or any major rise in water where flow has caused an increase in discharge and transport, we will go and collect more data. So the model is another important and unique feature of this project because organizations like the Chesapeake Bay Program and the USGS also use models to predict best management practice effectiveness by predicting the sediment load that will result from implementing these practices. However, the USGS uses traditional models like the estimator model, which is a stream flow-based regression. These types of models don't account for the variability that occurs when high transport events occur. So the Lee et al. Method model, which we will be employing and utilizing, is a turbidity-based model which uses temporal autocorrelation and heteroskedasticity to account for the variableness in these high transport events. It can be used to predict the total suspended solid concentrations based on the turbidity and conductivity data that the sondes will be collecting. Turbidity is noted to be a good proxy for total suspended solids, and it increases when discharge increases when total suspended solid concentration increases. This model has been found to have more accurate and precise predictions and makes it very useful to employ. So the model development begins by choosing the covariates. Our covariates will be things like turbidity and site and T20. T20 represents a turbidity value which is greater or less than 20 NTU, which is the water quality guideline value for turbidity set by Washington, D.C. Virginia does not have its own water quality guideline value for turbidity, and because Washington, D.C. has a similar environment to the rivers that we will be studying, it's a good value to use. From there, we set the temporal autocorrelation in sight using the autoregressive structure, and then a backward stepwise model selection will be used using the Akaika information criterion, and that's to identify the covariate that has the most impact on the data. After that, we will assess the predictive performance of the models using cross-validation, and then the models can be used to predict TSS using the data collected from the in situ sensors. So one of the impacts of this project is that by using in situ sensors, we can improve models and as well as our understanding of sediment and nutrient concentrations, as well as their effect on the local activity and stream health. Another major benefit is that it can be used in our methods, can be used in a variety of ways, including monitoring how effective different BMPs are and monitoring the pollution of the rivers to see whether something's working, whether something's not, and identify areas of higher pollution and whether something needs to be implemented. And lastly, this type of methods can easily be scaled up and implemented in a variety of different locations. And most importantly, there's the potential for real-time data because the sondes can project the data to a satellite, which can send it to a computer. So researchers have the benefit of real-time data, and they don't have to go out in the field to collect it. So some of the major takeaways is that Hazel Run, Rappahannock River, Chesapeake Bay are all highly polluted from humans. Rappahannock River and Hazel Run has not been well studied, and our proxy model method has major benefits, and the methods can be scaled up in a variety of ways for a variety of different uses. These are some of my sources that were mentioned in this presentation, and thank you for watching.